Hello all, welcome to the presentation for project number 5 on the sensing of pneumatically conveyed cold particles. Our team members are Ben Alexander, Aaron Chen, John Fisher, Johnny Kimmel, Nick Meekum, and Nate Vogt. Our advisor is Dr. Shad Roundy, and our sponsor is Pacificor. Pacificor owns Huntington Power Plant. Built in 1971, it's a coal-fired power plant that provides electricity to the Greater Valley. At Huntington, they need to be able to measure the amount of coal running from the mill to the boiler. This coal is conveyed pneumatically. So we are tasked to develop a system that can measure at least the relative coal flow rate between pipes, and ideally to give a quantitative mass flow rate for each pipe. The problem is that milled coal is extremely abrasive, so our sensor needs to be either very durable or entirely non-invasive, meaning it doesn't come into contact with the coal. Pictured here are some of the existing sensors at Huntington Power Plant. These sensors protrude into the coal flow and are worn away by abrasion in a matter of months. Replacing these sensors is both expensive and time-consuming. So many of the pipe flows are measured by hand using isokinetic sampling. Pacificor has asked us to develop a cheaper, more durable sensor. Above are the measurement methods that we investigated. Based on Huntington's requirements, capacitive sensing seemed to fit the bill, due to the fact that the electrodes do not contact the coal flow directly. The measurement principle is simple, and existing chips can be used to measure the capacitance. How does it work? 2 copper electrodes on either side of the coal flow form a simple capacitor, and the surrounding steel pipeline acts as an electrical shield. Coal has a higher dielectric constant than air, so as more coal enters the sensing field between the electrodes, the capacitance increases. The net dielectric constant between the electrodes, and hence the total capacitance, is a linear function of the proportion of coal in the pipe. So by placing 2 of these sensors in series along the pipe, we can track artifacts in the flow between the 2 sensors and estimate the flow velocity. This here is how a sensor would be constructed. From the inside out, you would need an abrasion shield, an insulator, the actual electrodes, another insulator, and then the pipe. Pictured here are our final prototypes. After we presented the initial prototype design and results to Pacificor, the engineering team recommended 2 sets of materials for the abrasion shield and insulation. The first is Nordbak, which can operate as both an abrasion shield and as insulation. The second is alumina hex tiles, acting as an abrasion shield, and RTV, which acts as an insulator. These are all materials that Pacificor actually already uses at Huntington and withstand the coal flow well. In order to test our prototypes, we used both horizontal and vertical test rigs. We used sand as our coal substitute, which has similar dielectric properties. We used stainless steel pipes, and our final sensors were calibrated by filling the sensing region with our testing medium. And we are in the process of obtaining flow velocity using time of flight measurements between our 2 sensor prototypes. Pictured here is the horizontal test rig. The horizontal test rig unfortunately did not allow us to achieve significant particle flows due to back pressure from the filter. We also had issues with static noise from the blower, and we had to abandon this design. Our vertical test rig worked much better. We used stainless steel pipe in tandem with the same feeder mechanism. The metal pipes are held together with rubber couplings, and our testing medium is fed from above, which falls through the pipe and into the storage unit where it's collected. Since we don't have back pressure or static buildup, in combination with the fact that we can achieve much higher particle loads, we are able to collect much more accurate and much more usable data from these tests. This here is a video of a typical flow test. On the left, we have the feed mechanism as it drains into our sensor prototypes. On the right, you can see the sand as it leaves the feeder mechanism. And on the top right, you can see the data being logged from our capacitance chip. In order to calibrate our sensors, we passed bags of sand with known mass through the prototypes. Here for the hex tile prototype, we passed the bags of sand about each time through for each weight through the sensor and logged the capacitance. And this allowed us to establish a trend between capacitance and the mass of sand passing through the pipe. The error bars you see here represent a 95% confidence interval. Using that relationship, this is an example of one of our flow tests using, again, the hex tile prototype. We calculated the mass from the capacitance we measured. The lines at the beginning and end represented when we started feeding sand into the prototype and when we finished. The noise floor here is extremely low, about 2.5 grams for the hex tile sensor. We calibrated the Nordbak sensor in the same way. Here you can see that the error bars are actually a little bit larger. That's likely due to the fact that the bags of sand tended to get caught on the rough surface of the Nordbak as we passed them through the pipe. Here is an example of a flow test also using the Nordbak sensor. What you can see here is that the noise floor is actually still very low, about 5 grams. Comparing these two sensors, we see that they're actually both accurate to within 5 grams, which corresponds to about a 2.5% error at the scaled flow rate. We've discussed with Pacific Core engineers and confirmed that both prototypes could feasibly be scaled up to the full pipe size at Huntington. We plan on repeating these capacitance versus mass calibrations using pulverized coal in the coming weeks. We're also in the process of integrating the time of flight velocity measurements using our 2 prototypes before the end of the semester. Following that, the next steps would be to build a full-scale prototype and to design a user interface for Huntington Power Plant. These last 2 steps are ideal material for a future senior design project.